So it is my pleasure to welcome Edoardo Lauria from École Polytechnique. So today our speaker will talk about conformal boundary conditions for free fields. So please, Edoardo, go ahead.
Thank you very much, Matteo. It's I'm very honored to give this talk in front of you, and thanks a lot for the invitation. And before I can say anything, let me just say, please do interrupt me at any time in case something is not clear or you just want to protest. It's totally fine. I'm happy to make it as much as interacting as possible. So, okay, so today I'm going to tell you something about these conformal boundary conditions for free field, and this is some topic I've been studying in the past few years together with these fantastic collaborators. And so today I'll try to make a story out of it. Of course, I will not be talking about 4 papers. It's just a story. So let me start with some kind of some simple motivations, and I would like to start by defining what I mean by conformal boundary conditions. So I will, by the way, sometimes call them conformal boundary conditions. Sometimes these are also called the boundary CFTs, and so on. So, or BCFTs. So sorry if I cannot be consistent with myself. Anyway, so the story is the following. So imagine you are given a conformal field theory in D dimensions, and you want to place it on a space with a boundary. So now for this talk, and for my interest I will be always considering this kind of spaces with boundaries. So we have just a D-dimensional Euclidean space, flat space, and the boundary is just a D-1 dimensional flat hyperplane, and there is one transverse direction, y. Okay, this is just the simplest possible boundary. And so of course you have to prescribe boundary conditions in order to put the theory on the space with a boundary. And so conformal boundary conditions are simply those special class of boundary condition that preserve the D-1 dimensional conformal symmetry along the boundary. So, which means that if you started with a conformal field theory, so invariant under SOD plus 1, 1, which is the Euclidean conformal group on the D dimensions, then in a presence of a D-1 dimensional boundary, flat boundary, so you necessarily break this symmetry down to SOD, 1. And what is SOD, 1? SOD, 1 is simply the conformal group acting on D-1 dimensions, okay? So this group contains D-1 translations, SO D-1 rotations, but also dilatations and special conformal transformations. So this is a definition, but this definition is very good because it describes the so-called surface critical behavior. So what is the surface critical behavior? So if you study order-disorder phase transitions in materials with boundaries, like for example, just classic a ferromagnet that is somehow finite in space. So you observe that there are new scaling laws and new critical exponents that appear near the edge of the material. And these critical exponents are new in a sense that they are not inherited from the critical exponents in the bulk of the material away from the boundary. So this in turn reflects in a very special type of, in a new kind of phase diagram of such a material. So this is the prototypical diagram. You can think prototypical phase diagram of, let's say, the 3D easy model with a boundary. So what happens, roughly speaking, is that, so you see the diagram is very different from what you expect for just the easy model with without the boundary, let's say at zero magnetic external magnetic field. So here, even if you tune your material to the critical point so that you are sitting at the second order phase transition in the bulk, you still have an interesting phase diagram as a function of this coupling kappa, which is, let's say, a surface coupling. Okay, it's the strength of the surface coupling with respect to the bulk coupling. And so you can hit even some boundary phase transition. So this red dot, okay, which is called the special, I think, special transition. Now, so this is all physics, real physics, in a sense. One can so the boundary conformal field theory in this case. So the conformal boundary conditions are somehow responsible for these three lines. Okay. So these three lines are in correspondence with the possible conformal boundary conditions of the 3D easing model. But beside that, my motivation for studying boundaries and more generic defects is that these objects, they just belong, they are just legitimate objects. They do appear and they do belong to the quantum field theory as as they do the local operator. So these objects are also very important in high energy physics. They're just a part of what the quantum field theory really is. Okay. So in this business of exploring conformal boundary conditions, one is usually interested in studying correlation.
Sorry, I have some. I'm just asking about the bulk.
Yes.
What does this stands for? Can you comment on?
Sorry, what?
Because here on the diagram we see the surface disorder.
Yes,
and
yes.
Bulk disorder, but for example, we don't see the fourth piece of possibility, which is the surface order and the bulk disorder. So no, the converse.
Right. So what happens here is that yeah, there is yeah, I think this is just what happens. Okay, so this is just for example the case of I think this is the prototypical example for the 3D easing model. So certainly there are other possibilities if you consider other types of models.
Okay.
What I'm saying is that in the case of the easing model, this is what happens. So there is this boundary phase transition, and if you are below a certain critical kappa, as you increase or lower the temperature below or above the Curie temperature, you have that the bulk and the surface, they order at the same temperature, while above this critical kappa, you have that they order at two different temperatures. But I mean, in general, it could be more complicated, right? I mean, so this is not the generic scenario, it's just for the Z2 transition in 3D. Is it clear?
Thank you. Yes, thank you. Thank you for the answer.
So, okay, so the natural thing to do is to study correlation functions of operators that are inserted along the boundary. So these are the so-called local boundary operators. And because we are saying that we are insisting on having conformal symmetry along the boundary, of course, these correlation functions, they are very similar. They are also constrained by this conformal symmetry. And so they will be just as similar as, there will be just the correlators of a non-local conformal field theory in one dimension less. Why non-local? What do I mean by non-local? I mean that this theory knows that it lives at the boundary of some higher dimensional space. And so in particular, there will be, for example, no conserved energy on the boundary. So there will be the only energy that is conserved is, it includes the whole system, so bulk plus boundary. So in particular, this means that, for example, for those of you that are experts on conformal field theories, I mean, there will be no boundary stress tensor, okay? So in a sense, this theory is non-local. But beside that, I mean, these theories that lives at the boundary of this bulk are perfectly fine they are just conformal. They are just so their correlation functions are just correlation functions of a conformal field theory, and also we know that conformal field theories are constrained by internal consistency conditions like unitarity and crossing, and so they do also these boundary conformal field theories. So the question is the following: imagine I give you a bulk conformal field theory of which I know everything. So the natural question is, what are its possible conformal boundary conditions? So is there a way to classify all the possible boundary operators that can exist in such a theory? So this question has been addressed, and so there exists a classification, for example, in the context of two-dimensional diagonal minimal models, or for a compact free boson or fermion. So if I give you a two-dimensional diagonal minimal model, so there is a list of possible conformal boundary conditions which can be associated to this minimal model. But this question is much more complicated in higher dimensions, because in higher dimensions, you don't have many of these important tools that you instead have in 2D, like Virasoro algebra, modular invariance, and things like this. So my goal for today is to actually try to make some progress towards a classification of conformal boundary conditions for higher dimensional CFTs. And of course, this problem is just extremely complicated. So I will tell you about I will explain some more general facts, but in general, ultimately, I will be focusing on on the boundary conditions for the simplest conformal field theories that you can place in the bulk, namely conformal boundary conditions for free conformal field theories. Okay, so in my system, the bulk of the system will be always just a free theory, and then I will be allowing for arbitrary boundary localized interactions, assuming that they will preserve boundary conformal symmetry. So this, as I will explain in the first part of the talk, this is an interesting set of theories. I mean, there is this class, although it's of course a simpler version of the problem, try to understanding this space of conformal boundary condition is just for free theories is a simpler problem, but still it's a rich enough class of examples. I mean, it's an interesting class of examples. It's an interesting problem still, and indeed we can construct many interesting examples. And also, as I will try to discuss, we can actually use a bootstrap approach, which I will discuss in the second part of my talk. Bootstrap approach means that I will be able to say something non-perturbative about such a space of theory without invoking any microscopic construction of such conformal boundary conditions, but only exploiting symmetry and consistency conditions. Okay. So I want to start with before entering the details of the non-perturbative treatment and so on and so forth, let me just start with the very basics. So let me describe the simplest conformal boundary conditions for the simplest free theory in the bulk, which is free CFT. So the free conformal boundary conditions for a free massless scalar in dimension greater than 2. So the theory I have in the bulk is this guy, is just a free massless scalar. And now, so we have to try to find what are the possible conformal boundary conditions for such a theory. So we have the equations of motion. So what do we do? We solve the equations of motion, and we look for what are the possible near boundary expansion. So what happens near the boundary? So as y goes to 0, so the Laplace equation constrains the possible boundary modes that are admissible. So there are only two possible boundary modes. So these two possible boundary modes, compatibly with the bulk equations of motion, are the following. You can have an operator that here it's called phi hat. So it's a boundary operator with dimension, the same scaling dimension as phi. So phi has dimension d half minus 1, the dimension of a free scalar in the dimensions. The other boundary mode is the normal derivative of phi evaluated at the boundary. So this is the other. So there are only these two possibilities. that are compatible with the symmetry and with the bulk equation of motion. And now the stationarity of the action, so imposing that the action is stationary, will kill one of the two modes. And in particular, at the end, you are left with either the Dirichlet boundary condition or the Neumann boundary condition. So the Dirichlet boundary condition is just the statement when you push phi to the boundary, phi evaluated at the boundary itself is 0, while the derivative of phi evaluated at the boundary is a dynamical field. And vice versa, the Neumann case is just when you push phi to the boundary, phi hat is a dynamical field, and del phi hat is equal to 0. So if you drop conformality, there are more possibilities. You can take combinations of these choices. But if you require conformal boundary conditions, these are the only two possibilities. So either Neumann or Dirichlet. So there is a similar story for a slightly more complicated case, namely, so if we study the free conformal boundary conditions for a free vector field, free Maxwell field in 4 dimensions. So this is the theory that you have in the bulk, just a 4-dimensional free vector with a theta term. So F tilde is just the dual. And now if you study the bulk equations of motion, so you have to impose the bulk equations of motion, the mu F mu nu equals 0, but also the Bianchi identities, the mu F tilde F mu nu, so the mu F tilde mu nu equals 0. And now it turns out that, so these equations of motion will also constrain the form of the near boundary expansion of the bulk field strength, F mu nu. And in particular, it turns out that if you push F mu nu to the boundary, there are only 2 possible allowed boundary modes. And these 2 possible allowed boundary modes, which here I call the J hat and I hat, are 2 conserved currents. So as you push F mu nu to the boundary, you're going to find only at most 2 boundary conserved currents. These conserved currents are basically, they have the following form. This is very schematic. You can think of J as being the electric current. So it's like the normal derivative of the bulk gauge field in the parallel direction A, evaluated at the boundary. And I hat is like the magnetic current. So it's like the parallel derivative of the parallel component of the gauge field evaluated at the boundary. So now, again, the stationarity of the action will actually kill one of the 2 boundary modes. So in the Neumann case, J hat is equal to 0, and I hat is a dynamical mode, and vice versa, in the Dirichlet case, I hat is equal to 0, and J hat is a dynamical mode. So the general...
So may I ask a question? Sorry,
Please.
If possible. So, so here, apart from Maxwell, you have this theta term, right? Is this theta is a constant, or is it a field in your case now, or?
No, theta is like so the theta term is like just an additional coupling constant, right? So
but theta is so theta is a constant.
Yes.
So it doesn't have any kind of dynamical.
It's a constant. It's not a field. It's like It's like as G. All right. So there is G, and so in fact, after all, later I will be rewriting this in a more convenient way in terms of a complexified gauge coupling. So. Right, so after all, there is just one coupling. It's a complexified gauge coupling which contains both G and theta. So you can think of theta as just a coupling constant that is compact. So it is, it's like between 0 and 2 pi.
Okay, thank you very much.
No, you're welcome. So the general lesson is the following. So that's so you can think of the free conformal boundary conditions for these free theories as just a case in which there is nothing on the boundary. All what you have is, some interesting, some theory in the bulk, and then there is nothing, there are no additional degrees of freedom on the boundary beside those that are coming from the bulk. And as a consequence of this, once we study the equations of motion and we impose the stationarity of the action, if you study the bulk to boundary expansion of the free field, you find at most 1 boundary mode. So here is the example of the free scalar field. we had, in principle, 2 boundary modes allowed by the equations of motion and the symmetry, O1 and O2. But here, let's say, if I choose Dirichlet boundary condition, this is killed. And so I'm left with the other one. So which means that there is a one-to-one correspondence, which with the, what happens in the bulk and what happens in the boundary. Now you are not surprised if I tell you that correlation functions of this remaining boundary operator are totally trivial, because the correlation functions in the bulk are trivial, right? So in a sense, these correlation functions are just, they form a so-called generalized free theory. So they factorized and they can be computed by Wick's contractions. So this also gives us an intuition on how to construct now interacting conformal boundary conditions. So now started from the free boundary conditions. Now we move to a more complicated case, the interacting conformal boundary conditions. And again, I'm just explaining the case of where the theory in the bulk is a free scalar, but it works also for other free theories. So the natural thing to do, if you want to construct interacting conformal boundary conditions, is to start with a free conformal boundary condition and couple it to some additional degrees of freedom that are initially decoupled and live on the boundary. So imagine, for example, you take a Neumann boundary condition for the free scalar, which means that if you push phi to the boundary, you are left with this boundary mode that I called phi hat. Okay. So of course, imagine there exists some decoupled d-1 dimensional CFT that lives at the boundary, and this theory has an operator called calligraphic O. So you can just imagine turning on a coupling between these two sectors. This is a coupling along the boundary. Okay. And now what happens? Well, initially, you started with Neumann boundary conditions, so which means that the del Wi-Fi was 0 at the boundary. But now what happens is that so if you recompute if you impose stationarity of the action, again, because of the edge modes, so because of the interaction with the edge modes, now d Wi-Fi is not 0 anymore, is equal to G times O. So of course, when G is equal to 0, you recover the Neumann boundary condition, but otherwise, this mode is generated dynamically. So now you may imagine that imagine that you just run the RG flow, the renormalization group flow, and you see where you end up. You may end up in a conformal fixed point where both these two modes that are allowed by the equations of motion and the symmetry are present. Okay, so this is like so this intuition can be extrapolated as strong coupling, and I apologize because of course I'm not being rigorous here. So this can be, what I'm saying here can be proven, and you can find it in my paper from 2020. But I will not discuss the non-perturbative proof. I'm just kind of discussing the outcome. So what happens is that so at strong coupling, what is true is that in a sense, so what is at strong coupling a interacting conformal boundary condition? Well, it's just a theory where, in a sense, all the boundary modes allowed by symmetry and by the equations of motion in the bulk boundary expansion of the free field do appear, right? And this is due to the fact that the boundary is not empty. So there are additional modes that can interact with the boundary modes of the free scalar. And so that after all both of them are generated. So which means that if you start with, if you push phi to the boundary, you find both O1 and O2, these two boundary modes. And these two boundary modes, they have to satisfy the bulk equation of motion, which still is valid in the bulk. And so particularly the bulk equation of motion will tell us that O1 and O2, they have their scaling dimension fixed. So O1 will have the same dimension of phi. You can think of it as being phi evaluated at the boundary, roughly speaking. So it has dimension d½ minus 1. And O2 will have dimension dy phi, so dimension d/2. But so the only non-triviality in this expansion resides in these OP coefficients, these fusion coefficients, okay, which tell you how much of O1 and how much of O2 are contained inside phi. And these coefficients, they depend on the boundary conditions, so they are dynamical coefficients. They are not fixed by the symmetry nor by the equations of motion. And you also can expect that because of all these complications, now the correlation functions of these boundary modes of phi, O1 and O2 will not be simply computable by Wick's theorem. So they are not trivial at all. So, okay, so that was kind of a generic story. I now try to elaborate a bit on this story by giving you some examples and try to convince you that to try to show how this works a bit in practice, and then I will try to conclude by saying something non-perturbatively. So again, feel free. Let me know if something is not clear or if these motivations or the general procedure is not clear. Okay, so. This is the first example I want to discuss. So, say this example is just so the hope is that you get immediately convinced by the fact that even if you have a trivial theory in the bulk, like a free vector, a free Maxwell field in the bulk, the boundary conditions, the conformal boundary conditions for such a theory can be wildly complicated. And this is an example that I've studied in a paper in collaboration with these authors a few years ago. So this is just, again, here we're just looking at, we're just taking four-dimensional Maxwell field, okay, in a space with a boundary. So this is the full action of the theory that is now written in a more fancy language in terms of the self-dual and the anti-self-dual component of the field strength, and then in terms of the complexified gauge coupling. So theta is appearing here. It's the real part of tau. So as we said, we have the bulk equations of motion, and the equations of motion will tell us that as we push the field strength to the boundary, we find two boundary conserved currents. So these objects are conserved as a consequence of the bulk equations of motions, so and the Bianchi identities, okay? So they are objects of dimension 2. And so these are, so if you start with free conformal boundary conditions, you are instructed to set, for example, J hat to 0. This will be the Neumann boundary condition, or I hat to 0. This will be the Dirichlet boundary condition. But now what we want to do is to construct interacting conformal boundary conditions. So we want to couple these free conformal boundary conditions to some additional theory living at the boundary that is initially decoupled. So there is a very natural way, very natural and universal way to do that. Imagine you start with Neumann boundary conditions. Say that J hat is equal to 0. So J hat equal to 0 means that the normal derivative of the bulk gauge field, let's say it's A. So the parallel component of the bulk gauge field evaluated at the boundary is 0. So the normal derivative of this guy is 0. So which means that if you take a parallel component to the boundary, this is just a dynamical mode that appears, so it's available. So you start with the Neumann boundary condition, and you couple this Neumann boundary condition with the degrees of freedom of a 3D CFT. Okay. Now, if this 3D CFT has a U1 global symmetry that is locally generated by, let's say, a current JCFT, then there is a universal coupling that you can write down. So for every 3D CFT with a U1 global symmetry, you can just couple this. You can just couple this 3D CFT with a U1 global symmetry with the Neumann boundary conditions for the free vector by writing down this marginal coupling here. This is nothing but a gauging, right? A 4D gauging of this global symmetry. So it's obvious that, I mean, by now studying so if you're now studying again the impulse stationarity of the action, So the initial Neumann boundary conditions are now modified, and now J hat, due to the interaction with the edge modes, J hat is not 0, it's equal to J CFT, okay? So very good. So this interaction defines interacting boundary conditions. Of course, these boundary conditions are not yet conformal, because one has to see what happens in the far infrared. So as you let the RG flow go, if you follow the RG flow. Okay, fine. What happens is that it turns out that this coupling here is not just marginal, but it's also exactly marginal. And the reason is because, in fact, this coupling is controlled by the complexified gauge coupling tau. And the complexified gauge coupling tau cannot renormalize because it's the coefficient of a bulk operator. So the coefficient of a bulk operator cannot get renormalized by boundary interactions as a consequence of locality. So the boundary interactions can only renormalize boundary interactions, okay? So then this means that this object is not only marginal, but it's exactly marginal. And so this coupling defines a family of conformal boundary conditions parameterized by the upper half plane. So the complexified gauge coupling, okay? So there is some nice lessons that we can learn out of it. So first, even in this simple case, if you allow for coupling, even in the simple case of a free four-dimensional Maxwell field, if you allow for coupling to some degrees of freedom of the boundary, you immediately find infinitely many possible conformal boundary conditions. There is a family, continuous family of conformal boundary conditions. They live in this upper half plane. This is very interesting. There is another interesting property of these conformal boundary conditions, and which is that, so now you may think the following. So imagine you are sitting somewhere in this, imagine you are given this family of conformal boundary conditions. How do you go back to the situation in which you decouple this? How do you go back to the original situation in which you find again a Neumann boundary condition and a decoupled sector? So how do you go to the decoupling points? Well, if you set, of course, tau to I infinity, sending tau to I infinity, it means sending G to 0. And so this is one decoupling point. It corresponds to undo this gauging, so to turn to 0 this interaction. And so if you set tau to I infinity, indeed, you recover your original, by construction, you recover your starting point, the Neumann boundary condition for the Maxwell field, plus a decoupled 3D CFT. But what is interesting is that there are actually infinitely many decoupling points, because in the bulk, you have electric-magnetic duality. And the electric-magnetic duality changes the definition of F and F tilde, as well as the definition of tau, the complexified gauge coupling. Tau changes, it's transformed with an SL2Z transformation. So it's just a fractional transformation. And it turns out that if you now set tau to minus Q over P, where Q are just coprime integers, so this seems to be a perfectly fine point where there is no decoupling. But in fact, this is precisely hitting the pole of this SL2Z transformation, so that this point corresponds to a certain tau prime going to infinity, I infinity, in some other duality frame. And so there are infinitely many decoupling points, and to each of these decoupling points is different, right? These are different points in this manifold. And so this is an interesting feature of these conformal boundary conditions that, in a sense, they also allow you to approach infinitely many three-dimensional CFTs with a U1 global symmetry by doing this procedure. So defining the BCFT and then go to to each decoupling limit. What you obtain is you obtain an infinite family of three-dimensional CFTs that are all related to the initial one by an SL2Z transformation. Okay, so that was fun, but yeah, after all, it was just to convince you that things, even for such simple theory, are definitely not trivial. So that's only what I want you to remember in a sense. And now, of course, I will try to tell you that moved by this. So I will try to convince you that instead, for a free scalar, things are trivial. So let's try to construct interacting conformal boundary conditions for a four-dimensional free scalar. So again, the strategy is always the same. So we try to couple the free conformal boundary conditions to some 3D CFT that lives of the boundary, some 3D CFT of which we have control, right? So a natural choice are the ON vector models. So these ON vector models are perfectly well-defined 3D CFTs. They are under control at large N. In particular, they come in two varieties. So we have the free ON vector models. They are just N free scalars, let's say as I goes from 1 to N. So the free ON vector models as well, just a theory of N free scalars, and the leading singlet operator in this theory as just scaling dimension 1, because a free scalar in 3 dimensions has dimensions as dimension 1/2. So this is dimension 1. The second possible variety is the critical ON vector models. These are just N scalars with quartic interaction. So this theory, it's an interacting CFT. It's solvable at large N in a 1/n expansion. And one can see that the leading singlet operator in the leading large N limit is called sigma, and it has dimension 2. Okay, so we have these two possibilities. So let's try to construct interacting boundary conditions. Well, we can definitely construct two possible marginal interactions. So if we start with Dirichlet boundary conditions for the four-dimensional free scalar, remember this means that if you push phi to the boundary, this means that there is one boundary mode of the bulk free scalar which is allowed. It's precisely dy phi. This is an operator of dimension 2. So there is a very natural coupling between this mode and the leading singlet operator for the free ON vector model, because this is also as dimension 1, so this is dimension 3. So this is a marginal coupling. This is one possibility. Another possibility is to take Neumann boundary conditions and couple these Neumann boundary conditions to the critical ON vector model. How? By writing down some coupling of this form. Neumann boundary conditions means that as you push phi to the boundary, there is an operator phi hat of dimension 1, and sigma is available in the critical ON vector model, and it has dimension 2. So this is a marginal coupling. Okay, this defines interacting boundary conditions. And now we can say, okay, fine, I am done. Now I just go to the infrared fixed point, and I'm about to find the interacting conformal boundary conditions. But this is not quite the case, because if you compute now the beta functions at large N for these two couplings, G and G prime, so you can working at large N, you can compute the beta function exactly to all orders in G and G prime. So you can look for the fixed points for these couplings, and you realize that the RG fixed points for these two models, they just correspond to free conformal boundary conditions. So definitely it happens that, for example, if you start with the case of Neumann boundary conditions coupled to critical scalars, you have this coupling that I define here, G prime. This G prime is marginally relevant, so it grows in the infrared, it becomes infinity. But infinity turns out to be a 0 of the beta function. So this is another fixed point of the beta function for G prime. And the theory when G prime is equal to infinity is exactly dual to the theory of a Dirichlet boundary condition coupled to N free scalar with G equals 0. So this theory just flows to this other theory. So actually, this theory flows to this theory flows to another theory that has a dual description. This theory flows to another free boundary condition, a Dirichlet boundary condition, and there is a dual description for this. So we discovered that it's actually highly non-trivial. You could write down something that seems to work at the classical level, and then at the quantum level, it just decouples, and you end up into a trivial, a free conformal boundary condition. So there is another interesting twist of this story. So of course, you expect these two 3D CFTs to be completely different, and they are completely different. They are related by some 3D RG flow. But what I'm saying here is that it is possible to approach, for example, the ON model by starting with the Dirichlet boundary conditions coupled to free scalar. So these three, or vice versa, these three models, I mean, these two three-dimensional theories are completely different if you view them as three-dimensional theories. But the moment you couple them to the bulk, so the moment you accept non-locality by coupling them to the bulk, well, this theory live in the same space somehow, in the same space of theories. Okay, so this is kind of an interesting. It's very similar to what happens also for this the boundary conditions for the four-dimensional Maxwell field. That you take different three-dimensional CFTs, you couple them to the bulk, and you end up in a bigger space that I call the B tau tau bar, where all these theories are just specific limits. This is very common in, well, this is actually very common. It's something we are very used, for example, in string theory. Okay, so, and this is another final example. So now you may expect that now you could say, haha, but okay, so the free scalar field is so trivial, so how do you expect ever to find ever something interesting? But okay, so in fact, so things are completely different if you consider the conformal boundary conditions for a 3D free scalar field with a two-dimensional boundary. Because in this case, you can actually find infinitely many conformal boundary conditions. So before we tried a few things and we failed. So with a four-dimensional scalar with a three-dimensional boundary, we just failed. We didn't find anything. Here, you try the first thing that you come up with, and it works. You find immediately infinitely many conformal boundary conditions on the nose. How? Well, just take a 3D free scalar field with Dirichlet boundary conditions. Now, in this case, taking Dirichlet boundary condition means that when you push phi to the boundary, there is a boundary mode that is dy phi, and this dy phi has dimension d over 2, so it has dimension 3/2 in this case. Now, there is a very natural thing you can do in 2 dimensions. There exist diagonal minimal models, these guys, and at large M, every of such minimal models have an operator like that is in the standard notation labeled like 1, 2. So a Virasoro primary labeled 1, 2, which has dimension 1/2 plus large M corrections, and 1, 3, another operator called 1, 3 with dimension 2 plus large M corrections. So like if M was equal to 3, for example, that will be the spin operator in the Ising model, and this will be the energy operator in the Ising model. So of course, this operator exists for every M, and here I'm just looking at their scaling dimensions for large M. So because of this, there is a very natural coupling, marginal coupling, that you can write down. So you can couple these Dirichlet boundary conditions to these minimal models in the following way. I mean, a natural thing to do is to couple dy phi, which is dimension 3/2, to the, let's say, spin operator of the mth minimal model. So phi 1, 2, because it also has dimension 1/2. So this will be a marginal operator. And then, of course, there is this guy. So the poor phi 1, 3 is itself marginal, so it will be generated, and it's there. Okay, so again, now this is a candidate marginal deformation, but what happens in the far infrared? Well, one has to study the beta function, the system of beta functions for G and G prime, and look for fixed points where look for possible fixed points where the bulk and the boundary are coupled. So this can be done at large M. And what we find is that in this case, we find some perturbative fixed points where where G and G prime are exactly of order 1/m. So these are points where the bulk and the boundary are coupled. And in a sense, you can think that they define large M minimal model boundary condition. So for every, when M is large enough, there is a way to couple these minimal models to some bulk and obtain a consistent and obtain a conformal bound, an interacting conformal boundary condition. Okay, so now this was as I mentioned, I want to now go beyond perturbation theory, tell you something about classification. So far I've been just constructing examples, but now I will be just try to forget about possible constructions and try to just explore the space as it is by looking for a consistent, by try to solve and exploiting the symmetry and the consistency conditions. So what are these consistency conditions? So this corpus of consistency condition is called bootstrap, something that it's well known in the context, for example, of two-dimensional minimal models, but it carries over also for higher dimensional CFTs, and also for CFTs with boundaries and defects. So in particular, this is called, in this context, we call it boundary bootstrap. So one of such consistency conditions, which are true for every boundary conformal field theory, is the following. So take a boundary conformal field theory where there is a bulk operator phi, not necessarily a free field, okay? Just an operator phi. And assume that this boundary condition has a certain boundary operator called psi k. Now, imagine you want to compute the bulk-bulk boundary three-point function between these operators. There are two ways of computing this object. In the so-called boundary channel, you can trade this three-point function for an infinite sum of boundary three-point functions between all the boundary modes that can appear when you push phi to the boundary and this external operator that you are taking. So here I'm just, just expressing this fact by, let's say, saying that I'm pushing phi to the boundary. I find infinitely many boundary modes of phi. These are labeled OI, and then I take the three-point functions. These three-point functions are conformal three-point function, and as such, they are characterized by some coefficient that here is called Fijk. So if I do this procedure, I find an infinite sum over all the possible exchanged boundary modes in these OPs. These these expansions, this bulk boundary expansion will be controlled by bulk boundary OP coefficients, these B phi I and B phi j. There are these three-point functions that weight this sum, and the rest will be some kinematical function called conformal block that is completely fixed by the symmetry, and it's computable. On the right-hand side, I can do something, however, very different. I can first fuse the two bulk operators together in the bulk. So I trade these two bulk operators for an infinite sum of bulk operators that can be produced when I fuse phi with itself in the bulk. So this fusion will be controlled by some OP coefficients that here are called the F phi phi O. And these fusion coefficients are just the characteristics of the bulk theory. They know nothing about the defect. Okay, whatever. And then, so when I fuse phi with itself, I obtain some operator O. And then I push this operator to the boundary. So I recover, I trade this three-point function for an infinite sum of bulk boundary two-point functions. But you see, what is important is now that this is a very complicated infinite sums, and we don't know in general how to solve it. But now, so the important conceptual point is that the left-hand side here doesn't contain information about the bulk, while the right-hand side here contains information about the bulk. So this is a constraint on a possible conformal boundary conditions for a given CFT. And the very good news is that, which is a slogan for me, is that when this boundary when the bulk CFT is the CFT of a free CFT, this can be solved analytically. Okay, so there is a very special sweet corner in which the bulk CFT is a free CFT, and we want to study conformal boundary conditions for a free theory where all this corpus of conditions can be solved directly. Exactly. So the example is, imagine take a free scalar field. Imagine you want to compute the two-point function of phi with any boundary condition. You see, as I said, as I told you, the bulk boundary expansion of phi, it's very simple because even in the most complicated boundary condition, you only find two operators, two boundary modes. So on the left-hand side here, you find only two blocks. And because the dimensions, the scaling dimensions of these boundary modes are fixed, the only unknowns are these coefficients, b1 squared and p2 squared. And it's not difficult to see that very similar thing happens on the right-hand side. So if you fuse phi with itself, you just have to use your free OPE, of which you know everything. So the first operator that is exchanged is the identity. The second operator that is exchanged is phi squared, and you have to take the one-point functions of these operators. So the one-point function of the identity is 1, and the one-point function of phi squared is completely fixed by the symmetry up to a coefficient that is called a phi squared, and it's dynamical. And finally, you can just solve this equation, and you find that you find a relation between b1, b2, and a phi squared. Okay, this is highly non-trivial. So, but it works. So in this case, it's actually simple, but it actually works more generically if you study, for example, this more complicated three-point function between a free scalar, and a generic boundary operator psi k, because now, again, because of the simplicity of the bulk boundary of P of phi, again, you can write down this bulk boundary bootstrap equation that I wrote before, but now you can solve it directly because on both sides, there are only finite many terms. So it's not an infinite sum of weird special functions, it's just a finite sum of special functions. So let me just tell you that one of the nice features of this is the following. One of the important consequences of this bulk boundary bootstrap for a free scalar field is the following. So when you push phi to the boundary, as we said, you're gonna find all possible three-point functions between the boundary modes of phi, which can be only O1 and O2, and psi k, let's say an external operator that you pick up, an external boundary operator that you choose. So in general, there are three sets of such three-point functions. So for every k, you have f11k, f12k, and f22k. f12k turns to be related to f12k. Okay, so these are all independent for a generic CFT, but the point is that the important consequence of this equation is that, in fact, all of these OP coefficients, coefficients have to be related to each other. They have to be proportional in a very specific way. So f11k is proportional to f12k with a function that here is called kappa1. And if you are interested, you can find this function in my paper, but it's just a ratio of gamma functions where the variables here are indeed the quantum numbers of this external operator. So for every k, you can compute this function. And for every k, you can compute this other function, kappa2, again, a ratio of gamma functions. So it's important. I mean, the consequence of the bulk boundary bootstrap for such a theory is that all such three-point functions are related to each other, and you can think of them, you can think of these relations as the necessary conditions that allow you to encode the bulk information into the boundary. So because you could solve all these bulk boundary bootstrap equations, you can just solve them, encode all the bulk information into the boundary, and then focus on the remaining boundary correlation functions. So we said So we said that the theory at the boundary is a CFT. So correlation functions of such CFT have to be crossing symmetric. And so these correlation functions, so for example, if you consider the correlation functions of the boundary modes of the free scalar field, which we know they exist in every conformal boundary conditions for phi, so they have to be crossing symmetric. This is just a statement that when you fuse, for example, when you look for the 4-point, let's say you want to compute the 4-point function of O1, O1, O2, O2. So you fuse O1, O2 and O2, O2 together. So this gives you an infinite sum over all the possible exchanged operators weighted by this product, F11K, F22K. These are the coefficients that I reported before. While in the other channel, you can fuse together 1 with 2 to obtain an infinite sum over weighted by this other combination of OPE coefficients. So the fact that these infinite sums on both sides must give the same 4-point function is a highly non-trivial constraint that is indeed called the crossing symmetry. And it's a constraint on all the possible data that are relevant data that are, so on the spectrum of operators in this, appearing in these sums and the OP coefficients. And again, it's an infinite, so this corresponds to an infinite set of equations for infinitely many variables, but so it's very difficult to solve it analytically, but we can at least attempt for a numerical solution because there are some rigorous numerical algorithms to find what cannot be a solution. So the game here is now to run the bootstrap strategy. So we can just, so this is a standard numerical bootstrap problem. We know how to solve it, okay? So you make some ansatz about the spectrum and you see whether these ansatz can or not satisfy these equations. And if it's not, you just throw it away and you try something else. And you systematize this procedure. It's known how to, I mean, there is a very well-known procedure how to do that numerically. I just want to emphasize that if we were only looking at some lower dimensional CFT, we only had to solve these equations, where now these OP coefficients are all independent. Now, because we are looking for, we are actually looking at some conformal boundary conditions. So we know that all these coefficients cannot be independent from each other as a consequence of these equations here. So the bulk boundary bootstrap equations that we solved analytically can be input, the result of this equation can be input inside this. And so on the top of this, this is a standard bootstrap problem that becomes instructed with infinitely many constraints coming from the bulk boundary bootstrap. And so it's very constraining. Okay, I just want to present some numerics. So this is what we do. So we can proceed and try to play this game to study conformal boundary conditions for a 4-dimensional free scalar field with a 3-dimensional boundary. Okay, so what do we do here? So as I said, all these boundary conditions are parameterized by one coefficient, a phi squared, the 1-point function of phi squared, which is non-zero generically. And so this a phi squared varies in an interval between the Dirichlet boundary condition. This is the value where a phi squared describes the Dirichlet boundary condition, and this is the value where it describes the Neumann boundary condition. All what is inside it's a so-called interacting conformal boundary condition. Now what we can do is, okay, let's assume that our conformal boundary condition has some operator, there exists some operator in the spectrum, in the boundary spectrum, with the spin 2 and some conformal dimension delta 2. What is the, for each value of a phi square, what is the maximal allowed value for delta 2 before I cannot solve the crossing equations? I can violate my constraints. This is the procedure that you can run algorithmically, numerically. And so you find that, for example, this space is highly constrained. So you find that in this white region, you cannot have any conformal boundary condition. This white region is a region of disallowed values for delta 2. So the space of conformal boundary condition can only be at most in this blue region here. What happens in practice is that the more you increase the number of equations that you consider, and the more this upper bound goes down. So eventually we may expect it to approach the value of 3, which is the unitarity bound, which tells you that there is nothing. So if you approach the unitary bound, it just means that the entire space is trivial. There is nothing. So there is no interacting conformal boundary condition. But this is not quite what happens, because it happens that that there is a feature here. There is a point that becomes stable as the more, I mean, and so this point, it's like it's maybe an indication that for this value of a squared and this value of delta 2, there exists a stable, and there exists a conformal boundary condition, of which, however, we don't have any intuition of how to construct it. So I see that it's 1 hour, but can I take 2 more minutes?
Yes, please go ahead.
Okay, thank you so much. So again, this is not. I don't want to claim that we found an interacting boundary condition. I'm just saying that, you see, this is the completely dual approach. So here we don't know how to construct microscopically such a boundary condition if it exists. We just see that there is a point here, a region here that seems to be consistent with all our assumptions, and it may be the indication of some theory that may be or may not be constructed. Okay, so for the case of a 3D free scalar, things are even more interesting. So here we have an additional parameter that has to be, we have to introduce for technical reason. This parameter is called delta 0. It's just the scalar gap above the identity. So we have to assume somehow that there exists a scalar operator with dimension delta 0 above the identity, okay, on the boundary. And so we perform exactly the same analysis, numerical analysis. We try to maximize the dimension of the spin 2 operator on the boundary as a function of a phi squared and as a function of delta 0. And we have to choose a value of delta 0 and for a phi squared. So you see that, again, the white region here, which is the disallowed region, for example, if you choose delta 0 bigger than 0, this is the minimal assumption, is the most agnostic assumption. So it's pretty small. So the exclusion region is pretty small, but the more you increase the scalar gap, the more you exclude the part of the region. And there is an interesting choice, which is assuming that this scalar gap is bigger or equal than 1, in which all the minimal model boundary conditions that I shown you before seems to, well, they seem to lie at the boundary of this allowed region. So let me tell you something more. So what happens is that we have, so I told you we have an explicit putative perturbative constructions for minimal models for a 3D free scalar field coupled to some minimal models at the boundary. There is a perturbative construction. So in particular, we can compute all these values, delta 0, delta 2, and a phi squared as a function of m, when m is large in perturbation theory. And we can just see where these models sit in this plot. And they sit exactly at these red crosses. So, I mean, this is just an indication. So the moment if you keep delta 0 bigger than 1, which is an assumption that works for all these minimal models up to m equals 4, the minimal value is m equals 3, okay? So you basically include all these minimal models. But if you start increasing the scalar gap, for example, you set it to be equal to 1.2, then suddenly this whole region becomes disallowed, and the only allowed region is this small triangle with a vertical drop and a sharp kink. So the position of this kink is very well predicted by the position of the minimal model boundary condition. Although we don't expect, of course, this prediction to be, the perturbative prediction to be valid, because we are extrapolating a large M expansion down to M equals 4. So, but it's still remarkable that in a sense, this kink, this sharp, this feature of the plot here, in a sense, it's kind of aligned to is aligned with the position of this prediction. It doesn't have to be true. So, okay, I just want to conclude saying that I presented like a systematic study, I think, of unitary and conformal boundary conditions in free theories. So my message is that there are so many interesting examples that one can construct, and some of those interesting examples are very surprising because they show conformal manifolds and dualities and whatnot. And for these particular theories, one can also try to attempt to really carve out the space of consistent conformal boundary conditions by using a bootstrap approach, meaning without referring to any macroscopic description, but only exploiting consistency conditions. I didn't have time to explain all the details, but I've shown you some numerical results for D and a 3D free scalar field with a 3D boundary and a 2D boundary, which shows that this space seems to be pretty much very constrained. And there are many interesting future directions. For example, try to repeat this study for other types of free theories. So try to repeat this numerical study for, I don't know, a free Maxwell field or a free fermion, or just try to study instead the space of interesting and consistent conformal defects instead of boundaries. Okay, so this is all what I wanted to say, and I want to thank you for your attention.
Thank you very much.
Thank you.
Thank you. Thank you very much.
You're welcome. I hope it was clear, and just please let me know. I mean, if you have any question.
So are there any questions? So maybe I have one question.
Please.
So at some point you have displayed this classification according to the dimension and so on. So is there any point in your diagram in which you can, in the previous slides, in which you can, let's see, put some model, some critical model with long-range interactions?
Fantastic question. Yeah. So thank you. Beautiful. Yes. So in a sense, all these minimal model boundary conditions, they are kind of a generalization of the long ranges in model. So all these minimal models, boundary conditions that, so for which we have a perturbative construction at large M, so these red crosses here, they are like, they are exactly generalizations of the long ranges in model. So you know that the long ranges in model can be described as a free scalar field coupled to phi to the fourth theory, basically, right? So, and this is exactly the same. So if you, instead of coupling to phi to the fourth, you coupling to some ON invariant theory, or sorry, this will be for the four-dimensional perspective, but in the three-dimensional perspective, of course, you don't have ON symmetry. You have to couple to the minimal models. But so okay, let's put it in this way. So yeah, so I don't know. It's such an exciting question that I don't know how to approach it. But so yeah, so the answer is yes. All these models here, they can have a Landau-Ginzburg description in terms of just like a version of the long ranges in model. In the case of the long range in model, you just couple the Dirichlet boundary condition with the M equals to 3 minimal model. So the perturbative description ends up here, but of course we don't expect the perturbative description to be correct for m equals 3, right? It's just the smallest possible value. So we don't trust this. In fact, there is some evidence that if you couple the long ranges in model to the Dirichlet boundary condition, you just flow directly to the Neumann. So there is an intuition. There is a paper of Slavarichkov and collaborators where precisely they prove, in a sense, using some consistency of phase diagrams of these theories, of RG diagrams, sorry, these theories, that the Dirichlet model, so the right value for this red cross here, which is the Dirichlet boundary condition coupled to the m equals 3 unitary and diagonal minimal model, should be actually here. It's going to the Neumann. And let's say if you try to repeat the same analysis for higher hems, you find this. And so I assume that these guys, they are all related to some long range model in 2 dimensions. I hope my weird answer was kind of understandable.
Thank you. So it's very interesting to try to understand which models can be behind this kind of.
Yeah. So from the statistical mechanical point of view, that would be extremely nice. I think. I just have a Landau-Ginzburg description for that, and it's literally this one. So you just take the phi 1,3. So are you familiar with this? Right. So this is literally what you have to do. So you have a free scalar field in the bulk in 3 dimensions. On the boundary, you have your mth diagonal minimal model, and then you turn on a boundary coupling of this form. And this boundary coupling, this combination of these 2 couplings, this interaction is marginally relevant, and it ends up in a perturbative fixed point when G is large enough.
I see.
And so if you want the only, we were not expecting these examples to exist. I mean, we just found them, but what is interesting, I think, is that in our analysis, I mean, these examples seem to, exist also at strong coupling. Because also, if you try with a free scalar, right? In order to explain this feature here, so the rule of the game is that when there is a feature, this feature of the feature of the plot, like a kink, may indicate some interesting theory sitting there. There is no proof of that, but it's like from experience is something that usually happens. So whenever you find a kink, you try to find a theory that has the features, the right characteristics for being the theory living at the kink. And with the 4-dimensional free scalar, we tried. I mean, every time we were looking for we were trying to cooking up some marginal deformation and then try to study the RG equations and try to go to the fixed point, we were always ending up in some theory that was either non-unitary or it was decoupled, pretty much as it happens when you try to couple the free scalar to the ON vector models. You end up in decoupled theories. So, sometimes you have the feeling that something can work because it works classically, but it does not. Non-perturbatively, it just becomes excluded, and this is what happens, what you can see here. Most of the theories that you can write down in this region, they will just end up being excluded for some reason. So it's highly non-trivial that for the case of the minimal model boundary conditions that I presented before, this seems not to happen. Because now, I mean, this upper bound seems to be quite stable, and you can now try to focus at this point and try to extract some anomalous dimensions. Once you tune to a certain point in the plot, you can also extract the spectrum of the putative theory that lives there, and you can compare it with the prediction from the minimal model, and you see it works very nicely. And of course, the more you approach the Dirichlet boundary condition, meaning the m equals infinity limit, I mean, all these dots seems to be very well, I mean, they seems to hold at strong coupling. So it's highly non-trivial. But sorry if I'm taking too much time. Apologize.
So thank you. So are there any questions? Any further questions? Okay, so if not, let's thank again our speaker, Edoardo.
Thank you so much. It was a pleasure.
Thank you very much for the talk.
And okay, so perhaps I see you one day in Paris.
Yeah, hopefully soon. I will be back in Paris very soon, so like this evening. So yeah, sure. It's very interesting stuff that you are doing. I mean, this is.
Thank you, Matteo. It's I hope it was understandable. I realize it's sometimes very technical. I apologize for not have been perhaps the most I don't know, clear. Sorry, I mean.
No, it was.
It was
indeed, it was a bit difficult to follow at some point for myself.
I guess that I mean, but people with the background in you know, theory or more general physics could follow. I mean, there is a lot of room for rigorous work in what you are presenting, I think. So even, I mean, the story of the distance between your crosses and the lower bound, I mean, this in some sense, I think could be very interesting also for mathematicians. So interested in this kind of questions. So
yeah, I mean, so what I'm saying is, so in a sense, so what I'm doing here, I'm a bit cheating because in a sense, so conformal field theories can be defined, you know, more or less rigorously. And when I say rigorously, I mean that usually mathematicians are happy with the definition of the axioms of conformal field theory, because yeah. So and so the existence of these internal consistency conditions, like the crossing equations and the bulk boundary bootstrap equations, it can be established at some mathematical level with some level of rigor. Mm-hmm. Then of course, so what I'm not really using, you know, this fact. I'm just exploiting these equations because I know that this procedure is kind of rigorous. So I know that it's in a sense, I know what are the assumptions that I have to make, and so then it's when I said that this kind of search is very agnostic. I mean, it in a sense it's true. So that's the only let's say mathematical approach that I could actually advocate. That has been advocated in this case. Then in practice, yeah, everything else, like this distance, I mean, it's something that it's, you know, you are comparing some perturbative description that is not supposed to work because, yeah, it's only supposed to work around m equals infinity and you are looking at finite m, so it's not supposed to work. But you're comparing it with some bound that you obtained numerically. And so there is another black machine, I mean, black box, which is your computer. So where you kind of literally try to solve this infinite set of equations. And so it's you know, it's a bit difficult to, how do you compare the two things? Like the two things separately are not, so the upper bound is rigorous. It's really rigorous and you can prove it mathematically. But you know, the position of the dot is not rigorous. There is no reason for it to be there. What is interesting is that there is a proof of concepts that is to see whether I mean, it could be very well that after all, when you try to study this set of equations, you end up in a completely empty space. This is what happened for the case of a four-dimensional free scalar field. And then it will be very interesting to prove it mathematically. Why is this such a case? This is the case. And for example, in the case of we also studied the problem for conformal defects for a four-dimensional free scalar field, and there one can rigorously prove it. I mean, there is no need of invoking numerics. You can literally just solve all these consistency conditions and use the tool of non-perturbative quantum field theory to prove that literally, to prove that the space of conformal boundary conformal defects for such theory is just empty. There are no interesting theories. I can send you if you want the link. But I think for defects, there is certainly a lot of rigorous work that can be done. But of course, every time you kind of invoke the numerics, it's just cannot be that rigorous. That's all what I wanted to say. But it's definitely interesting, yeah. And yeah, by the way, this was you can try to make it more rigorous if you include more structures. So for example, in the case when you want to study conformal boundary conditions or conformal defects for 2D minimal models, diagonal minimal models, then the classification is really possible because you have so many additional structure. You have the Virasoro algebra, you have modular invariance, and so then you literally have to, you go to each of these constraints and you just solve them and you end up in a complete classification. For higher dimensions, this becomes perhaps possible if you include additional symmetry like supersymmetry or things like this. But even in the simplest theories, like just a free conformal boundary condition for free fields, yeah, I think already finding that most of the space has been excluded, I think it's from the conceptual point of view, it's highly non-trivial. Anyways, thank you for the questions. It was nice.
Okay, so thank you again, Edoardo. So for the others, we will see each other, I think, in 2 weeks. There will be next talk.
Okay. Bye-bye.
I'm not sure. Thank you also for your effort to be more understandable. Thank you so much.
Well, I don't know if I made it. I mean, because honestly, I apologize. I mean, I just want to apologize because I read I've seen, for example, that Pietro Benetti Genolini gave a talk in the previous speaker, and I kind of I watched the talk and in a sense I was I think we are more or less in the same field, so I imagine that it was that kind of the style of presentation was fine. Then I know Matteo, but of course it's just a guess. Then after all, one has to extrapolate, and as we know, extrapolations are very rarely rigorous. So I apologize, but I hope at least the context and the physical motivations are kind of clear. Then yeah, I cannot talk for a mathematician, or I'm not rigorous as a mathematician. So I really made an effort, but I don't know whether it worked.
Yeah, I think it worked. In all cases, it's recorded, and I think it would be beneficial for someone. Yeah.
Erase it.
It would be beneficial for someone.
Don't tell me. Anyway, I'm happy to, if you have any other questions or
yeah, actually I have a question, but I was worried that it is a stupid question. So
oh, come on, please.
Yeah, it's not, it's just a remark about you have showed a diagram which shows the half circles. So, and it makes me remember the geodesics of the half Poincaré half plane, hyperbolic. So there is some relation with this decoupling problems and.
So you're saying that
I don't know if you.
No, but I think yes. I mean, so okay. So I think I know what you're. Well, I don't know if I can intercept your question, but certainly I know what is the
yeah, yes, this one. Yeah, this.
I mean, the thing is that I think so there is a I mean, this is a conformal manifold, so it's a space that is spanned by the exactly marginal deformations of a given quantum field theory. So say the tangent vectors of this space are operators of dimension 3. And in such a theory, in this theory, so the Maxwell field with a boundary, there are 2 of such tangent vectors. And in fact, there is even a complex structure, okay? Because these vectors are like, they are either chiral or anti-chiral in a sense. So there is a complex structure that is inherited from the fact that the gauge coupling is complex. So I think the metric along this space is hyperbolic. Okay. So I'm not completely sure because, of course, it's a bit difficult. I mean, so the metric on this space, it's well, now that I told you what are the tangent vectors, you can figure out what is the metric. The metric is given by the 2-point functions of these the 2-point correlation functions of such tangent vectors. This defines an object that is called the Zamolodchikov metric, and it's a natural metric for spaces with the conformal with the exactly marginal deformation with the conformal manifold. So the point is that this object, so this metric itself, is not exact in a sense that its precise value depends. I mean, changes order by order in perturbation theory, right? So when you compute that, for a given theory, you compute it at 3 level, you get some number, and then you get corrections, quantum corrections. So this object in this case is, but I think at 3 levels, so at the first level in perturbation theory, I think this is kind of just an hyperbolic metric. So when there were you, so just to tell you, so this, okay, so what does it mean? It means that the fact that there are these singularities, the fact that there are these rational cusps, this is not going to be, this is going to be unchanged. So because the fact that there are these cusps is a property of the fact that there are these decoupling limits. So these are singular points and they are always singular. But the fact that there are these very nice circles, this may change. Because I don't know really. I mean, this is just this is basically just a plot of the hyperbolic plane with these cusps and these nice. It does not represent really the marginal but yeah, I mean there is a relation, of course, at 3 level at least.
So maybe I can add an input for Ayman. I think it's related to the fact that the group SL to Z, if you look at the orbits in the hyperbolic plane, then the areas that stay in the same orbit, which are the areas, each triangle in the plot that Edoardo showed us, has the same should have the same area in hyperbolic coordinates.
Yeah, that is true.
So in a sort, this is a tessellation of Poincaré disk, what we are looking at.
It's true, yeah. So this is just, yeah, so, okay, exactly. I think...
sorry, Matthew, for a moment, you have... do you hear me? Do you hear me?
Yeah.
Okay. Yeah, you have said that the orbit, the orbit, if you take a triangle, and then okay, I got some cutting in your voice, so I didn't follow what you have said.
I said that each triangle that you are able to identify in this plot has the same hyperbolic area.
Yeah, so this is just so this is just a picture, of course, of all possible choices of the fundamental domain of SL2Z.
Yeah.
So which means that if you are so now I don't remember, but so each triangle is a fundamental domain, right, Matteo?
Yes.
Each triangle is a fundamental domain. So if you take points in this triangle here, for example, also by acting with an SL2Z transformation, you will map each of these points inside this triangle in somewhere outside, but you will cover the entire upper half plane.
Yeah, but some kind of tailing of the
but
of the space.
Yes, but this is not. I mean, so yes, so that's certainly true. However, I mean, in a sense, indeed, this is just a picture of. This is just a picture of these choices. I mean, of the fundamental domain, but in practice, I mean, it's not. This is not physics. I mean, that is not really representing a marginal. Marginal. Yeah, I think I don't know now. It's not so. Yeah, I think I should just say, as Matteo said, that this is only representation of SL2Z.
Okay.
Right, a representation of the fundamental domain of SL2Z. And the only point I wanted to add is that these rational cusps, physically, they correspond to points in which the boundary and the bulk decouple. So this corresponds to singularities of the physical theory. So that's that was also just my point.
Thank you very much for.
No, it's a pleasure. Thank you. Okay, very good. So bye.
Have a good day, and hopefully see you soon.
Yes, you too, guys. You too.
Thank you.
Bye.
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 Bye.